Hi, we are Group 10. Today we are going to do our presentation for BRT 1333 Advanced Electrical Circuit. Group members. I am Stephen Paul David, matrix number B122410461. Augustine, matrix number B122410440. Ahmad Iqmal, matrix number B122410518, and Rineshwar, matrix number B122410723. Contents. First is introduction. The transfer function, also known as the network function, is a valuable analytical tool for determining how a circuit responds to various frequencies. In fact, the frequency response of a circuit is the plot of the circuit's transfer function against which changing from to a transfer function is the frequency dependent ratio of a force function to another forcing function, or an output to an output. When we used impedance and admittance to relate voltage and current, we implicitly introduced the concept of a transfer function. In general, a linear network is represented by the block diagram in figure below. Part A. Transfer function. The general state of equation to get the Bert plot. H omega equals to j omega plus 10 over, in a bracket, j omega close bracket open bracket j omega plus 5 close bracket power of 2. First step you have to do is factorize the equation. So h omega will be 10 bracket j omega over 10 plus 1 close bracket over bracket j omega close bracket 5 open bracket j omega over 5 plus 1 close bracket 5 open bracket j omega over 5 plus 1 close bracket. Then you have to simplify the equation. So you will get h omega equals to 0 times 4 open bracket j omega over 10 plus 1 close bracket over bracket j omega close bracket open bracket j omega over 5 plus 1 close bracket open bracket j omega over 5 plus 1 close bracket. Magnitude plot. H omega equals to 0 times 4 open bracket j omega over 10 plus 1 close bracket over open bracket j omega close bracket open bracket j omega over 5 plus 1 close bracket power of 2. First, you have to substitute the value in the formula below to the above question. And then you have to identify the factor and magnitude of Bert plot. Next, I will give it to my teammate, Rineshwar.
Hi, my name is Rineshwar Manikamani, matrix number B122410723. So I will present by continuing the magnitude plot. In this slide, the first constant is 0.4, which affects only the magnitude. So we calculated it by using the equation 20 log 10 into 0.4, which gives a constant negative gain. The phase stays at 0. Next, we have a simple 0 at z equals to 10. It increases the magnitude slope and by positive 20 dB over decade after omega equals to 10. For the phase, it gradually rises to positive 90 between omega equals to 1 and 100. For the expression, 20 log 10 into 1 plus j omega over 10. So for this slide, it itemizes the same element. We can see their individual effects. The constant 0.4 we do the fixed downshift with no slope. 0 at 10 radian per second will be 20 dB per decade by gaining beyond omega equals to 10. So the pole at the origin will be to the negative 20 dB per decade from the start, and at last the pole at 5 radian per second will be to the negative 20 dB decade, where starting at omega equals to 5. So basically this is the final expression we get for magnitude dot plot. And let me break it down this to step by step. By the first term, 20 log 10 times by 0.4 represent a constant gain which gave us a starting in a sense of decline of approximately negative 8 dB. The second term, 20 log 10 times by 1 plus j omega over omega corresponded to a 0 at omega, which introduced a rising slope of 20 dB per decade in the dot plot. And then the third term, which is negative 20 log omega times by j omega, represent a pole at the same frequency, effectively cancelling out a rising caused by the zero. This flatten the slope back to 0 dB per decade. And then the fourth term, which is negative 20 log times by 1 plus j omega over 5, and the fifth term, which is negative 2 log 10 times by 1 plus j omega over 5, expanded as represent two additional poles at omega equals to 5. Combined, they contribute a total slope of negative 60 dB per decade after that frequency. These combinations of terms is what defines a shape of the dot plot magnitude we explored in the next slide. Now this is the graph we get it from magnitude dot plot for the transfer function we just analyzed. Starting at the low frequency, the dot plot begins at around negative 8 dB, which is due to constant gain term for 20 log 10 times by 0.4 we discussed earlier. At omega equals to 1, the zero starts to take effects and introduce a positive slope for positive 20 dB per decade. However, this immediately cancels out by the pole at the same frequency, resulting in a flat gain response at the region. We reached omega equals to 5. The two poles at the beginning of the influence the slope. The first adds 20 negative 20 dB per decade drops, and the second adds another negative 40 dB per decade, making the total of negative 60 dB per decade beyond this point. These transitions are clearly marked out where the dot plot we label slope, helping us to visualize how the formula and the translation into frequency response behavior. So for the next part, we will do a phase dot plot. We begin with the transfer function h omega equals to 0.4 times with j omega over 10 plus 1, and then over j omega times by j omega over 5 plus 1 power of 2. And it's the space we have to calculate by using a formula theta over inverse tangent inverse times by omega over z1. This shows us we will be analyzing the phase by examining each component contribution through inverse tangent function. The equation reveals three key elements affecting phase at 0, where omega equals to 10, and pole at origin, and also the double pole where omega is equal to 5. So each will be contribute different to the total phase shift. So this is a table help us to understand the component. The first component is the constant 0.4 contributes 0 phase shift at all frequencies, as all the positive real constants do. The second is our 0 at omega equals to 10, follows the standard simple 0 pattern by starting at 0 phase shift for low frequency and reaching out for positive 45 phase shift at omega equals to 10, and approaching positive 90 phase shift at high frequencies. And thus we can reach the 90 n notation, since we have a 1 0 where n equals to 1, the maximum phase contribute will be positive 90. So now we will examining our poles, and the pole at origin 1 over j omega give us a constant of negative 90 phase shift. The double pole at omega equals to 5 is more complex, being squared by n equals to 2. It is phase contributes a range from 0 at low frequency through the negative 90 phase shift at the omega equals to 5. At negative 80 phase shift is the highest frequency, because since we have negative 45, we have to times with 2. This table confirms that the poles create phase lag with the slope and the final multiplying by n for repeated poles. So this is the last expression we get by combining all the components. We get the phase equation, which is theta equals to 0 degree plus tangent inverse multiplied by omega over 10, then minus 90 degree, and minus 2 tangent inverse multiplied by omega over 5. Let's break down this. The first 0 is the form of our constant. Then the tangent inverse multiplied by omega over 10 is our zero's positive contribution. And the negative 90 degree is the fixed pole at the origin. And lastly, the negative 2 tangent inverse multiplied by omega over 5 is our double poles amplified effect. This equation allows us to calculate the accept phase at any frequency. So this is the graph, and the graphical results show us the phase progression starting at negative 90 degree from the pole at origin. It makes the steep transition around omega equals to 5 due to the double pole reaching about negative 153 degree at omega equals to 5, and the 100 negative 180 at omega equals to 10. The zero cause a slight nil near omega equals to 10, but can't overcome the dominant pole effect. The final value is the negative 180, which has important implication for system stability and performance. So this is the last part, which is zeros and poles. From this equation, we can observe the key characteristics of the system. At the numerator contains 0 and omega equals to 10, which will introduce a positive slope of 20 dB per decade in the board plot. And in the denominator, there is the pole at the origin where omega equals to 0, which contributes a negative 20 dB per decade slope. Additionally, the term where j omega over 5 plus 1 power of 2 indicates two repeated poles at omega equals to 5, resulting a combined slope at negative 40 degree dB per decade starting from that frequency. So that's all from me. Later, the part B will continue by my teammate.
Hello, my name is Ahmad Ikaman. Today I'm going to explain about the boot pole. First, we have a graph where the x-axis is hdb, and the y-axis is omega radian per second. First, our line start from 0 radian per second to 100 radian per second with the flat response of 0 dB per decade. Next, for 100 radian per second to 1000 radian per second, the response become a low frequency of negative 20 dB per decade. Next, our last point is 1000 to continuous is it became from negative 20 dB per decade to 0 dB per decade. Next is the calculation to identify the plot given. First is step 1, which is from from 0 dB from 0 radian per second to 100 radian per second. First we have first the formula is 40 equal to 20 log k, and with simple math we can move 40 with the log and become log k equals to 40 per 10. And then with after dividing 40 with 10 become 2, it become log k equal to 2. And after moving the log to the other side, it will become k equal to 100. Next is step 2, which is the the line here from 100 radian per second to 1000 radian per second. First, we have our value is negative 20 dB per decade and omega 100. The formula that we will use is either JW per 100 plus 1 or 1 per 1 plus JW per 100. Both equation works, but the most effective one is probably the second one. Next is our step 3, which is identify simple zero positive, which is the flat line over here from 1000 to the continuous radian per second. First, our value is 0 dB per decade and omega 100. We also have two equations, which is either JW per 100 per 1000 plus 1, or H omega equals to 100 plus JW per 1000 per 1 plus JW per 100. Both equation works, but the most effective one is this, of course, the second one. That's it for me, and I will let my group mate continue.
Hello everyone, my name is Augustine Lucky David. So I'm going to present the discussion and the conclusion. So first we go to discussion. So in discussion, in part A, we work with a given transfer function and broke it down to understand how it behaves across different frequencies. Okay, first, zero and the pole impacts. We identify a zero at 10 rad, which caused the magnitude flow to rise at 20 dB per decade. Then we also saw a pole origin, which introduced a constant negative 90 phase shift and a negative 20 dB slope in a magnitude plot. Additionally, there was a double pole at 5 rads, making the slope even steeper at 40 dB beyond this point. Second, we find out the mode plot behavior. The magnitude plot showed clear slope changes at these critical frequencies, confirming our calculation. The phase plot reflected expected shift to 90 degree from the zero and the negative 90 degree from each pole. Okay, moving to part B, we did the reverse, starting from a board plot and extending the transfer function. First, we spotted a zero at 100 rad slope increase and a pole at 1000 rad slope decrease. By analyzing the magnitude levels, we calculated the gain constant to complete the equation. Okay, next we move on to conclusion. This assignment has provided a deeper understanding of how transfer function related to frequency behavior of electrical circuits. To the analysis of question B, we prioritize, factorize, and simplify a complex transfer function, identifying its poles and zeros, and consulting both magnitude and phase plots. This demonstrates the impacts of multiple poles and zeros on the shape and the slope of a plots. For question H, we reverse engineer a both magnitude plot to determine corresponding transfer function by observing key features like slope changes and corner frequencies. We accurately located the poles and zeros and derived the mathematical expression of the system. That's from me. Thank you.